Hello, and thank you for joining today's Tech Insights webinar, Recent PMIC Innovation and Automotive Market Outlook. We will get started in a few minutes. My name is Jianchun. I am the Product Manager of Power at Tech Insights, and I'm here to introduce our presenters and tell you a little bit about Tech Insights. Today's presentation will be delivered by Dr. Steve Russell, subject matter expert for power at Tech Insights, and Asif Anwar, executive director of the Powertrain, Body, Safety, Chassis, and Electric Vehicles Service. This presentation was previously recorded, but you can submit questions to be addressed during the live Q&A session at the end of this webinar. Just click the Questions tab and enter your question in the text box. We will answer all the questions live at the end of this presentation. I will hand it over to Steve and Asif shortly, but first, I'd like to provide a short introduction to Tech Insights. Tech Insights is the most trusted source of actionable, in-depth intelligence related to semiconductor innovation and surrounding markets. By revealing the innovation others cannot inside advanced technology products, we provide competitive technical intelligence through reverse engineering to inform product roadmaps, market analysis to de-risk strategic investment and procurement decisions, and IP service. And now I will turn it over to Dr. Steve Russell.
Hello, I'm Stephen Russell. I'm Power Semiconductor Subject Matter Expert at Tech Insights, and I'm going to talk you through the first half of today's webinar. Split into three parts. Firstly, I'll look at our Power Management IC roadmap and some exciting breaking news for some technology we've recently observed in the market. Part 2 will focus on mobile PMICs with some innovation we've seen in integrated voltage regulator technology, specifically looking at two examples we've seen in the Apple MacBook M1 Pro, the 2021 model, and a device from Empower. The final part, part 3 of my section, will focus on automotive PMICs, and we'll see the variety of technology in this space. Part 1, Roadmap and Breaking News. Before we dive into our roadmap, a very quick refresher. What are we talking about when we talk about PMICs? And what is the BCD process? PMICs are power management integrated circuits, and their applications are numerous. They can span from single-digit volts to potentially over 1,000. And applications include mobile, industrial, automotive, and even high voltage gate drivers. All BCD devices are PMICs, but not all PMICs are BCD, as we'll see a little later in the presentation when we talk about the integrated voltage regulator technology. So we see on the right of the slide here an example from ST Microelectronics. ST claims to have invented the BCD process back in the 1980s. BCD, by its very nature, is power management, and it contains three different technologies on a single chip: bipolar, CMOS, and DMOS. Digital, analog, and power. Digital for signal processing, analog for interaction with the outside world, and power for power conversion or driving external load. The logic nodes of the CMOS does lack cutting-edge pure logic ICs, but the real innovation here is making sure you can fabricate all these technologies on a single device. And the isolation between the digital and the power components is key, as they can be operating at 10 times the amount of voltage. We see on the bottom of the slide examples of each technology that we've observed in the market. So a bipolar junction transistor, the analog component, the digital CMOS logic. This is a special type of power device, a drain extended MOS. And we finally see on the right the different types of isolation, here all on this single chip, low cost, STI and DTI. Onto our roadmap. So given that the applications of PMICs are so vast, it's difficult to have a single track roadmap. There's different tracks you can take in terms of different technologies. These can be split broadly into high density with small logic nodes and PMICs that are focused on high power. Also a kind of overlap between the two is becoming more and more important, automotive PMICs, achieving automotive qualification and working in this environment. So there are different needs. High density. Many process innovations have enabled the creation of LDMOS transistors on the same die as logic, without compromising thermal budgets for digital components in the processing. High power. Different technologies are required to handle these powers, such as thick copper interconnects. So looking a little bit more detail then at the high density roadmap, we can see the BCD technology process shrink, where we're achieving increased logic density. This has gone from well over 180 nanometers in the early days, but looking more recently down to 130, 90, 65, and now 45. Different manufacturers are at different stages, and this isn't a definitive list, but it's where we've observed some of their technologies. There's an aside here, integrated voltage regulator technology. Again, not a BCD process, but achieving a power management kind of application. Here we've observed a 12 nanometer FinFET process for this technology. We also start to observe memory incorporation into PMICs, volatile and non-volatile memory, with examples of resistive RAM and phase change memory, either in the market or on the horizon. A lot of different processing innovations happen, going from this 180 nanometer all the way down to 45 nanometer we see today, such as different silicide processes. We've also seen other technologies incorporated, such as capacitor integration, moving to copper metallization, low-K intermetal dielectrics, and some of the things we might expect to see as we go even further, metal gates. So 45 to 40 nanometer process is the smallest we've observed to date, but we know companies are pursuing even smaller nodes, and 20 nanometers even has been mentioned by TSMC. I mentioned previously about different isolation technologies, such as low-cost, shallow and deep trench isolation, and incorporating multiple isolations on the same die. Automotive has a slightly different requirement. It's not so much about the most cutting-edge technology node, but really ensuring the highest amount of safety and reliability for the devices. And depending on the application, such as system critical, we're seeing increased redundancy and increased complexity of the safety protocols for technologies such as ADAS towards full self-driving electric vehicles. Finally, just touching briefly on the high power, we see different sorts of isolation such as resurf and SOI, silicon on insulator. We're also observing things like galvanic isolation on chip, 1200 volt capability, and perhaps one day in the not too distant future, we can talk about gallium nitride technology as a true PMIC. Some exciting breaking news. Wireless charging ICs is where we're seeing some of the most cutting edge technology in terms of PMICs. The iPhone 13 Pro was capable of 15 watts wireless charging. This is impressive, but obviously some way off the latest wired charging. For example, Xiaomi have a 120 watt capable model of wired charging. We expect to see continued significant improvements in wireless charging in the coming years, with 30 watt on the horizon. Moving to smaller node BCD processors allows for more dense, complex logic integration. And the integration of memory into these technology allows for interplay with the software algorithm to actively monitor and ensure peak battery charging efficiency and lifetime of the battery itself. So in the iPhone 13 Pro model, we observed a Broadcom wireless charging receiver IC, and this is also in the iPhone 14 Pro model released this year. Looking inside this product and the die found within, we can observe complex circuitry, which we'll begin to analyse over the coming slides. It has hallmarks and fingerprints of a TSMC process, and we can see from the die markings it was manufactured relatively recently with a 2020 date code. For more first look details and much more, do check out our Disruptive Technology event linked here. From our exploratory cross-sections, we find the logic region has a contacted gate pitch of around 160 nanometers, the metal 1 pitch of around 130 nanometers. Both of these are indicative of a 40 nanometer logic process. Finally, the right-hand image is one of several candidate bipolar junction transistor structures found on this die, suggesting a BCD process. Also for our subscribers, a PMIC process analysis report is underway, which will contain full SEM cross-sections, TEM cross-sections, dopant analysis, and much, much more. Finally, looking at an image of the die deprocessed to the polysilicon level, we have performed a basic high-level block analysis. We can see analog, digital, and power elements across the die. See analog regions 1, 2, and 3 here. 3 different power transistor blocks, and our digital block. We also observe memory regions, M1, 2, and 3. M3 has been identified as SRAM, but if we look at TSMC's product release for 40 nanometer BCD, they also mention they're adopting resistive RAM as an industry's first. We are carrying out investigations to try and identify that on this die. One final thing to be aware of in terms of process innovation is for BCD for TSMC's 40 nanometer process, i.e. what they're terming their high end, they've also moved to 12-inch wafer fabrication. Even within high-density logic PMICs, we still observe a large variety of logic nodes available within the marketplace. And it's not necessarily the case that smaller is better. It's really application dependent, and more specifically, power level dependent. As you increase the power level of these products, the die becomes more and more dominated by the power transistor regions, and hence there are diminishing returns and logic shrinks. So let's take a quick look at a couple of other examples we've observed in the market. A Samsung 130 nanometer logic nodes PMIC, the SPS26, from the Galaxy S22 Ultra phone. There are some interesting observations to note from this product. There's a sort of crossover between 130 and 90 nanometers. We would expect, as we go down to 90 nanometers, copper metallization to be used. This product has a contacted gate pitch of 400 nanometers, indicative of a 90 nanometer node, but we still see aluminium metal used. This isn't the only case that we've seen as well. So we speculate that several manufacturers are still trying to use aluminium metallizations down at these nodes. Looking at a slightly different example from Maxim, now Analog Devices, a true 90 nanometer PMIC. And we can see here copper metallization being used. The previous record holder for lowest logic node we have observed in a BCD PMIC also came from the iPhone 13 Pro. This is a Cirrus Logic amplification device. We observed in this product a contacted gate pitch of 260 nanometers, indicative of a 55 nanometer process. We believe this to be likely GlobalFoundries 55 BCD light process. And for our subscribers, a report is linked here. Some notable features include the use of copper metallization and nickel for the silicide process. Part 2. Further mobile PMIC innovation. Integrated voltage regulators. Where a traditional voltage regulator circuit would comprise a PCB with an associated PMIC and passive components, integrated voltage regulators attempt to shrink this down to a single product, saving on both board space and bill of materials. We've looked at a couple of examples of this recently, and this technology is developing at quite a pace. This product from Apple, the APL 1028 IVR, was found within the 2021 16-inch M1 MacBook Pro. And we can see when opening up the package, on top of the PMIC device is an inductor array. We can see in more detail in the SEM image on the right-hand side how these copper bars surrounded by a magnetic envelope are formed roughly in the RDL region of the device. There's a recent publicly available blog where I discuss in more detail this and other examples of integration, from early attempts by Intel all the way through to what we are seeing today. The actual PMIC die itself resembles more of a logic IC than a traditional BCD PMIC. And we should note there's no traditional LDMOS style power devices present here. It is still controlling power management, however, at a relatively low voltage, estimated to be around 2 volts, but with high current to supply the components within the MacBook Pro. Our measurements indicate this PMIC uses what's likely the 12 FinFET process from TSMC. A TEM cross-section of the power block can be seen on the right of this slide. We see different arrangements of fins in different blocks, so this power region has up to 20 fins all aligned. Now a similar concept from M-Power Semiconductor, a packaged IVR solution with triple output, so outputting 6 amps, 2 amps and 2 amps with a total of 10 amps output, again for roughly 2 volts. There's no on-chip inductor present here, but we can see within the package itself, looking at the X-ray here, there's 4 accompanying capacitor die with a cross-section of these seen here, formed by deep trenches in a silicon die. M-Power do offer a couple of solutions in terms of integrating an inductor. There's the EP7037C, which we completed a PMIC report on earlier this year, where they offer a custom-made service to co-design with you a PCB with an inductor trace. Or the EP7037B, which actually contains an inductor wound into the FCBGA package itself. Again, now looking at the main IC die, so labelled the TRIO PMIC die here. Like the Apple product, this die resembles more of a logic IC than a traditional PMIC, although again, it is serving power management purposes. It's a complex 12 metal copper process, not BCD. Again, we believe this likely to be the 12FF process from TSMC. And similarly to the Apple IVR device, we see different arrangements of fins in different blocks, depending on the function. Part 3, Automotive PMICs. I mentioned during our roadmap discussion towards the beginning of this webinar how ST Microelectronics claimed to have invented the BCD process back in the 1980s. Well, last year they were awarded the IEEE Milestone Award in recognition of this. Today their platform maintains nodes from 320 nanometers down to 90, with 40 in development. Looking closer at their offerings, it tracks well with our own roadmap, with the different tracks available for different applications, such as the higher voltage, higher power, and the higher density. It also illustrates that smaller logic node and higher density isn't necessarily better. It's not a one-size-fits-all, different technologies for different applications. So for example, we see these higher voltage and the SOI variants for applications such as motor drives, whereas the high density is more mobile consumer level. Of course, there's a plethora of applications in between, and there are important subdivisions even within automotive technology. And I'm going to show two examples of this in the coming slides. The BCD8S auto process, 160 nanometers, and BCD9S, 110 nanometers. These serve different voltage classes. Looking firstly at the ST Microelectronics A6985F synchronous step-down switching regulator for automotive applications. We see the die, pretty much the top half of it, is dominated by power devices, with logic taking up smaller regions on the lower half of the die. So, given how much the power device takes up, shrinking the logic any further isn't really necessary for this case. We can see the logic transistors feature a contacted gate pitch of around 790 nanometers, indicating a process node of around 160 nanometers, and likely ST's BCD8S auto technology. It uses aluminium metallization, and we can see a bit more detail here in terms of the large LDMOS transistors present in the top half of the die. Features both an NLDMOS and PLDMOS for synchronized on-off control to regulate output voltage. And some of our analysis can be seen on the right of the slide here, such as a logic cross-section, a TEM image of the LDMOS power transistor, and dopant analysis of this transistor. Now on to another ST product. Still an automotive application, but a very different one. A Class D audio amplifier, the FDA801B. You can see the die here. We found some notable design wins for this technology. For example, we found it within a Bose amplifier in a 2021 Hyundai Ioniq electric vehicle. It uses a copper metallization process, and the logic transistors feature a contacted gate pitch of around 620 nanometer, indicating process node of 130 and likely to be ST's BCD9S technology. There are multiple LDMOS arrays at the top and bottom of the die, but not taking up as much overall die real estate as in our previous example. There are some other notable innovations we observed here. For example, it's the first time we observed low-cost STI and DTI isolation all on the same die. See here around the power device, the low-cost STI and DTI regions. A publicly available blog chronicled the evolution of STMicroelectronics BCD technology over the years. We've been tracking this for almost 20 years, all the way back to 0.8 micron nodes. The final example of our automotive PMIC analysis I want to show today is from NXP. We see here a system basis chip. These are far more system critical than, say, the audio amplifier example we saw in the previous slide. They're critical for controlling power to the drivetrain or automated driver assist technology, requiring much increased redundancy and safety. There's also a more stringent qualification level. These products are rated to Automotive Safety Integrity Level D. Hence, it features a 250 nanometer node, so lagging the cutting edge, but becoming highly integrated in terms of these redundancy features. As autonomous driving levels increase, so will the need for redundancy. This system basis chip, for example, features fail-silent operation. NXP have a roadmap going over the next 10 years in terms of increased safety and eventually security features that will be included in these types of devices. Our high-level functional block analysis of the N84R die found within this product shows the complexity of circuit integration in this type of product. For example, we see here the fail-safe machine, multiple power transistor arrays, analog components, and also various different interfaces such as CAN and LIN to interface with other automotive systems within the vehicle. Wrapping up then, the technical process analysis portion of this webinar. We see logic shrink of standard BCD high-density PMICs continuing, and there's still some way to go yet. Manufacturers are pursuing 40 nanometer nodes and beyond. There seems to be a crossroads approaching at around 20 nanometers, however. This is about the time that logic ICs moved from a planar gate process to FinFETs. Will we see the same thing happening in BCD? At this stage it seems unlikely. Integration of FinFETs with traditional planar type LDMOS transistors would seem to be prohibitive and introduce a lot of complexity into mask design. We believe there will be more bespoke integrated solutions, such as what is already appearing in the market, as in integrated voltage regulator technologies. And it seems there will be different products and different nodes for different applications continuing, with even the high logic node variants not completely disappearing from the market. Also in this vein, automotive PMICs may lag the cutting edge process-wise, but they have stringent safety protocols and will see even more complex integration in these parts moving forward to deal with increased safety and reliability required by self-driving technology. This is only scratching the surface of the PMIC analysis that Tech Insights offers. We see here a couple of other examples, such as industrial bipolar stepping motor driver ICs in the bottom left, and an SOI-based gate driver from Infineon in the bottom right. Thank you for your attention so far, and I'd now like to hand over to Asif, who's going to handle the market analysis portion of this PMIC webinar.
Strategy analytics is a market research capability focusing on the technology markets. My focus is on the automotive sector, and I specifically lead the powertrain, body chassis and safety service and the electric vehicle service and channel, which will be which will underline and underpin the material that we'll be presenting today. So what I want to do is to look at the overall outlook for vehicle production and the associated system demand, and then also discuss some of the impact that macroeconomic factors may have on the future outlook that we present. I'm then going to dig a little bit deeper into the automotive sector, starting off with a general overview and then breaking that down into an outlook for PMIC devices. And that will be followed by conclusions and some Q&A. So if we look at the automotive production numbers, then what I'm presenting to you here today are the quarterly numbers as published in Q3, just at the beginning of October. And I'm also making a comparison with the previous quarter's numbers as well, just to give you a sense of how much the forecast has or hasn't changed. So you can see here that the overall numbers are fairly well aligned, and we're expecting to see 82.5 million units being produced in 2022, increasing to around 102 and 103 million units by the 2029 timeframe. What we have noted is that compare this to the earlier forecasts in around the January and February April timeframe, then you will have seen that the overall outlook is about 3 to 5% lower. Now, despite that downturn in forecast outlook, what we're seeing in the overall system demand is actually an uptick. So you can see overall that by that 2029 timeframe, we're actually expecting to see a 2.3% uplift in the overall automotive electronic systems dollar demand by 2029. And this is primarily being led by the moves towards electrification in the automotive industry, and specifically an assumption that we will continue to see increases in the penetration of battery electric vehicles. There's also some impact as noted as it relates to the move towards domain-based architectures, and specifically here as the penetration of domain-based architectures for infotainment systems in particular. Now, there are obviously some risks to this outlook. The COVID situation has been an ongoing risk for the past 24 months or so, and continues to be a factor that needs to be played into the future outlook, especially as certain countries have zero COVID policies in place, which have impacted the supply chain. China is a good example of this, and we saw this earlier this year as the supply chains around automotive production in places such as Shanghai effectively shut down for a quarter. The other area, obviously, that we continue to have issues around is with respect to semiconductor supply. So what we've noted here is that the overall issues around the supply-demand imbalance continue to remain in place, and is something which we start to see some form of normalization towards the back end of 2023. But in the meantime, it is going to continue to have an impact on the overall outlook for automotive production. And finally, perhaps the biggest impact has been the Ukraine conflict. This has not only had a devastating impact on the region itself, but it has also had an impact on the global economy, starting off with the energy disruption that happened around Europe, and then spreading globally into a general global economic slowdown, which has led to further supply chain disruption. If I take a closer look at the Russia-Ukraine impact, then we can see here that we can address this along 4 key areas. Number one has been the potential brake on electrification. And this has been caused by the potential supply chain disruption of key materials such as nickel, as well as an impact on how well you can continue to look towards alternative chemistries and materials. We've also seen the impact on semiconductor production earlier in the year. So neon supply, which was a byproduct of Russian steel manufacturing, is used for photolithography. And so we saw companies which are key suppliers of this gas being impacted as that Ukraine conflict, as the conflict started to impact the Ukraine. In Russia itself, obviously, we see the impact to light vehicle production. And by now, pretty much all of the major international OEMs that were operating in Russia, both in terms of selling vehicles as well as producing vehicles, have effectively pulled out. And in terms of a market, then this has also impacted those companies, those OEMs who focus on, rely on Russia as an export market for their premium sector models. And finally, we've seen this impact on the technology development within the automotive sector as well. So companies that were operating in Ukraine have had their operations disrupted as a result of the Ukraine conflict. And this has impacted both software development, battery technology, as well as in-vehicle infotainment capabilities as well. So those are factors really that we see more on the production side. But the biggest risk potentially moving forwards, at least over the next 18 months or so, is really the consumer. So the rising inflationary pressures that we're seeing on the consumer has effectively meant that that discretionary income that a consumer may have had, which would have allowed them to make a purchase of a brand new vehicle, is no longer there. Especially in Europe, consumers are much more worried about being able to pay their gas and electric bills. And so the prospect of buying a new car is something which is being offset, at least for the time being. So what we expect to see potentially is that there will be an impact on production, not as a result of some of these other factors. Those factors may start to alleviate themselves, but even if they do, then we see a replacement from the supply side where the demand is just simply not going to be there, and that will then impact vehicle production moving forwards as well. What we do try to do is to present scenarios in the short term as to what those impacts could be. So what you're seeing on the right-hand chart there is in the blue bars are the standard scenario based around the light vehicle production forecast, which I presented in the earlier chart. And what you see in the lines, the green, blue, and red lines are the scenarios that could be presented. And you can see particularly the extension of the Ukraine conflict has a significant impact on the outlook for 2023 automotive system demand. Now, I realize as I say this that we are in a situation where the Ukraine conflict seems to be turning in favor of Ukraine, and we've seen some gains. But we have to factor in the uncertainty around Russian intent and what they're willing to do to save face effectively. And so there is still that potential risk moving forwards. And that's something which we will have to continue to factor in as we make our forecasts for both the automotive production as well as the associated system and semiconductor and sensor demand. So with that said, what I want to do is to look at the automotive semiconductor outlook. But before I do that, I thought it would be useful just to kind of present to you the automotive playbook, as it were. And just really to kind of highlight some of the key differences that we see within the automotive sector versus supply of semiconductors into the commercial and consumer markets. And the key, most significant point that we see here is obviously the need for qualification. So functional safety, ISO 26262, and the requirement to be able to ensure that your semiconductors are able to meet the operational requirements in terms of temperature, noise, vibration, and EMC are all unique to a certain extent to the automotive industry. And certainly those requirements are nowhere near as strict as you would see in, for example, the commercial markets and the mainstream consumer markets. The other side of this is that we see a very long product life cycle, both in terms of development time as well as in terms of the overall life cycles themselves. So whereas in the consumer market, we've generally noted that, you may be changing a phone every 18 to 24 months, the expectation is that the automotive platform is going to be around for at least 10 years. And so you need to be able to, as a semiconductor supplier, be able to support those long life cycles. The other side of this is you still have very, very low volumes. So 85 million units or 82 million units increasing to 110 million units or so is peanuts if we compare that to the mainstream smartphone market as an example. But what's been, if you like, characteristic of the automotive industry is that they have continued to require pricing to be reduced on a year-on-year basis until very recently. Obviously, right now we're in this semiconductor shortage, and so if you like, the power has shifted towards the semiconductor suppliers. But prior to that, there was an expectation that every 2 or 3 years, every year or so, you would need to a 2 to 3% decrease in your pricing ASP. And also, generally speaking, the automotive industry has tended to be a technology laggard. So in terms of process nodes, we've typically seen the automotive industry lag behind by at least 12 to 18 months versus what we're seeing in the commercial and consumer markets. And given the long product life cycles and the long product and the requirements for long product support, that has also required the semiconductors to have some form of obsolescence management in place to be able to maintain that support moving forwards. If we look at this visually, you can see the differences in terms of operational parameters across the temperature range, the operating lifetime, the failure rates that are acceptable in the automotive industry versus the consumer market, and also the supply lifetime that is expected for those semiconductor components. So we can translate all this into kind of some of the requirements and success factors if you do want to be operating in the automotive semiconductor industry. So number one, at the end of the day, is that long-term planning is needed. If you're engaging with customers, it won't be for the next year's tranche of production. It will be engaging with customers and looking to get onto their platform in the next 3 to 4 years. So you're designing for that next design cycle, which might be the manufacturing year in 2024, 2025, or even beyond that, 2027, 2028. And part of this is the fact that the qualification itself takes time. So the semiconductor devices may be there, but you need to be able to ensure that they are going to meet the AEC-Q 100, 101 requirements. They are going to be able to meet the functional safety requirements, and that in itself takes time to be certified. You should also expect volumes to be low, while also seeing that your customer actually wants you to offer volume pricing. And within that, the whole concept of longevity is a core requirement. So your supply and support needs and capabilities need to be able to extend for 10 plus years. And once you've been able to do all that, then the upshot of this is that you have a long-term contract which will extend for those 10 plus years, and those design-ins will then extend to multiple platforms. So the aggregate volumes will build up over those years and provide you with a stable outlook for your semiconductor content. Now, we talked about electrification at the beginning of the presentation, and you can see that as we break the market down in terms of where the demand for semiconductors is going to come from, then electrification and the associated trends around ADAS in particular, as well as advanced infotainment capabilities, are really going to drive the semiconductor demand over the next 5 to 10 years. So you can see in this on the pie charts here that by 2029, 50% of automotive semiconductor demand is going to be directly attributable to the electrification market, as well as to demand from ADAS systems. If we break that market down further into the devices themselves, then we can see that trend very much being repeated. So in terms of the processor side, you can see that there is a shift away from microcontrollers towards more complicated, more capable SoC-based solutions. And this is going to be driven a lot by the demands from ADAS, as well as demands from advanced graphic requirements coming from infotainment platforms, and which will require the need for multi-core SoCs. We're also obviously seeing the move towards domain-based and zonal-based architectures, which will also shift the demand towards highly capable SoC-based solutions that are able to begin to virtualize some of the non-safety critical functionality that have typically been encompassed in standalone ECUs. From a power perspective, obviously, the push towards electrification is going to drive that demand for power devices in particular. And within that also, we're seeing this move towards wide bandgap semiconductor technologies as well. And that is providing with some automotive semiconductor companies with a whole new breadth of opportunities in that particular sector. And related to that, we see linear devices. And linear devices in particular are being driven by demand from ADAS, where the requirements for radar will drive demand for RF-based componentry, and also for in-vehicle networking, where we see the push towards domain-based and zonal-based architectures driving that move towards Ethernet-based solutions. And in the electrification sector, obviously, as well as the demand for power management ICs, we also see a significant demand for battery cell management capabilities. And that's going to be addressed by increasing demand from an ADC perspective as well. So you can see the overall market for semiconductors is going to continue to grow and reach around about $110 billion by 2029. And if we break that down into the linear device market, within which we have our PMIC sector, then we can see that that is approaching around about $22 billion in that same time frame. In terms of automotive semiconductor supply, we see Infineon, NXP, and Renesas as the market leaders. And over the past couple of years, we've seen some shifting in the number one and number two position. So Infineon gained the number one position as a result of its acquisition of Cypress Semiconductor a couple of years ago, and it maintained that in the 2021 timeframe. But what we did see was that in 2021, NXP did make some ground on Infineon. And a large part of that can be attributable to some of the semiconductor shortages that we saw in 2021. So Infineon in particular was affected by the Austin snowstorms, which impacted their automotive revenue. And this was not necessarily the case with NXP. So you saw that impact being reflected in that closing of the gap between those two. We've also seen the emergence of newer players, such as Qualcomm, who are now starting to really make an impact on the overall market share as they drive their capabilities into the infotainment, ADAS, and overall electrification and market, and leveraging their family of solutions across the board, and also leveraging acquisitions in the software area as well. Moving forwards, we can expect to see that the acquisitions that we may see moving within the automotive semiconductor supply chain will need to be focused on strategic areas such as electrification, connectivity, ADAS and autonomy, and infotainment and telematics. We're also seeing a changing in the overall supply chain dynamics. So we saw at Electronica 2022 the announcement that Stellantis would be working directly with Infineon for its supply of silicon carbide semiconductors. And that's something which has been reflected in general across the board. We've seen other announcements from NXP, from Qualcomm and other companies where they are touting the fact that they are working directly with an OEM for the supply of semiconductor components. And it really kind of reflects the importance that semiconductor technology is now playing in the drive towards electrification and the associated trends around ADAS and automated driving, as well as advanced infotainment and telematics capabilities. If we take a closer look at the PMIC market, then very much the companies who are providing that BCD technology are the very same companies that we see being the main providers in the overall automotive semiconductor market. So we've highlighted companies such as ST, NXP, Infineon, Rome, Texas Instruments, Renesas, and Toshiba. And at the same time, you're also seeing foundry companies also providing automotive grade BCD process capabilities to their customers. So companies including TSMC, Global Foundry, UMC, Tower Jazz, and X-FAB. So there's obviously a supply there, and when we break that down into the power management market, then we see a market which is approaching $3 billion by that 2029 timeframe. So just to give you a little bit of context behind the numbers, we don't specifically break out the PMIC, and we really count that as being part of the VREG market. And generally speaking, this is because the power management IC will usually typically have multiple VREGs integrated into it. The key demand, if we break this across the domains in terms of powertrain, body, chassis, safety, and driver information, is really coming from the safety demand. And you can see that the safety demand, and specifically ADAS, is driving a compound annual average growth rate of around 18%. Compare that to 10 to 12% for the body, chassis, and powertrain domain, and it's almost twice the growth rate of PMIC demand from the driver information sector. And as we've seen in the previous chart, the majority of analog semiconductor vendors are providing and supporting this growing market moving forwards. So that brings me to my conclusions. In terms of vehicle production, we see 2022 output stabilizing. Overall volumes are now hitting around 82.5 million units, which is a little bit up on the previous expectation, but the overall growth is still a little bit negative than we have previously forecast. And obviously some of the macroeconomic factors that we have highlighted, such as the semiconductor shortage, ongoing zero COVID strategies by countries such as China, as well as the Ukraine conflict, have a potential to continue to impact the outlook moving forwards. The other outlook changing factor there is going to be the supply side of things, where the inflationary pressures are making it more difficult for the consumer to make buying a vehicle a priority in the next 18 to 24 months. Having said all that, xEV adoption is now a key underlying factor for growth in both the system demand as well as the associated semiconductor demand. And so those new xEV platforms are effectively at the leading edge of all the architectural change that we will see that will underpin the other automotive sector trends. In this context, we see the automotive semiconductor market growing to $112 billion almost by 2029. That also includes the semiconductor-based sensors. And we've seen that the electrification and ADAS in particular accounting for around 50% of that demand by 2029. The PMIC market is going to be driven in particular by the ADAS demand, which will see growth of about 18%, and a market in total worth about $3 billion by that time frame. And the long-term outlook for automotive industry remains very, very strong. So even though we might see some slowdown in vehicle production, the overall trends towards electrification coupled with ADAS and automated driving, as well as the moves towards the connected vehicle, still remain in place, and they will continue to shape the system, semiconductor and sensor demand for the forecast period that we expect to see moving forwards. So with that, I would like to thank you for your time and attention, and I'll be happy to answer any questions that there may be. Thank you again.